Recording. So I'm going to start recording now. I wanted to go through some more curve sketching examples, and then we'll talk about optimization. I put up the homework also. Homework number 7 is posted. As you'll know in the unit notes, there are no questions. So what we're doing is we are moving to some exercises from a textbook. I set it up online so that you can download the textbook exercises and the answers to the odd problems. And then I assigned 4 odd problems for you to do. So it looks a little bit different, but they're all the files are available online and for free. Additionally, what I did, I know that a lot of people have been struggling with the material, and part of me wishes that we had gone with an online homework system. I really wanted to save people money, but I know that it's also hard not having that instant feedback on your homework. So one thing I really highly suggest to people is Khan Academy. Khan Academy is a completely 100% free resource. If you don't know the story behind Khan Academy, if you've never heard of Khan Academy before, Khan Academy was started by this guy who wanted to teach his niece math from across the country. And so he posted videos about math on YouTube. And those videos were so successful that he ended up getting endorsed by a lot of nonprofit organizations and was able to make Khan Academy's website. The website runs a lot like online homework systems do, but it's completely free to both educators and students. So you go on and it's kind of like a game system, like you get mastery points for like watching videos and taking quizzes. So if you're somebody who's really motivated by that style, I know I'm a person who's motivated by getting little badges or getting awards for like watching videos or doing stuff like that. I highly, highly suggest Khan Academy. Their videos are really great. They might do some things differently than how I do them. I'm not too concerned about that. You can always do things differently as long as the math is correct. Personally, myself, they go up pretty high in math. So when I was in a class that's a little bit past calculus, it's called linear algebra. It sounds like it's an easy course, but it's a higher level math course. Very fun. But I only passed that class because of Khan Academy. So I can endorse it. That was in my undergrad, which was many years ago at this point, which is weird. But I only passed that class because of Khan Academy. Khan Academy absolutely got me through it. I understood everything so well because of it. Someone says, "Ugh, I have to take that class next year." I actually loved linear algebra. It's a really fun class. So if you have to take it, honestly, I like it better than calculus. So it's fun. It's fun. You'll be okay. I promise. But Khan Academy, great resource. Highly suggest it. So anyways, they have related rates problems. They have optimization problems, which is what we're getting into next section. I think they have curve sketching problems. They have all types of things. So just highly recommend it because it's a free resource out there for you. Okay, enough of me chit-chatting. Okay. Clicking record again. Now click. Okay. I'm not going to let that happen to me again. Let's go now. So I went online and I have some problems online that I found. The hard thing with curve sketching is that a lot of these numbers don't come out nice because the way you have to imagine for a curve sketching problem to come out nice, the first derivative has to factor and the second derivative has to factor. So it's very, very difficult. In fact, if you want a challenge, you could try to create a problem that works. It's very, very difficult to create good, nice curve sketching problems. So I looked online and I found a few that'll work for us. Let's see. There we go. So what I'm going to do is we're going to start with a polynomial, and then we are going to do a rational function that's already been factored and stuff. So sketch the graph of f of x equals x to the 5th minus 5x plus 1. Unless we already did this one. Let me just go check my notes to make sure this wasn't like one that was also in our notes. Just going to double check. No. Okay. All right, so with curve sketching, the first thing we're going to look for are x-intercepts, y-intercepts, asymptotes, and any domain issues. So the nice thing about polynomials, which this is, right? This is a polynomial. The nice thing about polynomials is they have no domain issues and no asymptotes. That's just a nice thing. No horizontal, no vertical, no slant, no anything. So you don't have to worry about any asymptotes. But we do have to worry about intercepts. So for the x-intercept, that's when you're setting y equal to 0 and typically factoring. So you have x to the 5th minus 5x plus 1 equal to 0. This one's actually not a nice one for finding the x-intercept. This isn't going to be a nice one to solve for. So what I'm going to do is use a, see if I can get, no. What I'm going to do is use Wolfram alpha to get my intercepts for this guy. So I'm just going to give these to you. Used online calculator. So I typed in this exact equation to an online calculator. If you have one where it's really just not going to be easy to factor, like it's not like a quadratic or anything, it's okay to use a calculator in that scenario to find the zeros. To find, so we find that x is equal to 0.2 is a 0, negative 1.5-ish, and 1.4-ish. They can't all be winners. So then plugging those x values, you plug those x values that you get back into the original equation to get your points, because we want coordinate points that we can plot on our graph. So this is going to be approximately, in this case, y is approximately 0. So you get the point 0.2 comma 0. In the case of negative 1.5, you'll get that y is approximately 0.9. And in the case of 1.4, you're going to get that y is approximately negative 0.6. The y-intercept is easy in that all you have to do is plug in x equals 0. So 0 to the 5th minus 5 times 0 plus 1. you get 1. So you have a y-intercept at 1, 0. Sometimes it helps to kind of box off the information that's important. So these are our x-intercepts. Here's our y-intercept. And then from here, we're going to be doing increasing, decreasing, maxes, and mins. So you take the first derivative. So why isn't it scrolling? There we go. Our original function right here, we take the first derivative. We get 5x to the 4th minus 5. Set it equal to 0, and we're going to make a sign chart. Why are you not moving? There we go. We're going to make a sign chart. So we can factor out a 5. We have x to the 4th minus 1 equal to 0. Somebody said, oh, yeah. Somebody said, hey, Miss Cook, pay attention, which would be completely fair. No, that's not what they said. They said, isn't it 0, 1? And the answer is yes. Thank you so much. I appreciate you catching that. All right, so back down here. This is actually a difference of squares. It's like a secret difference of squares. It's x squared minus 1 times x squared plus 1. So you could see that the middle terms would cancel here. And then you have an x to the 4th minus 1. As a note, x squared plus 1 does not factor. Sum of squares do not factor. But x squared minus 1 does. It factors into x plus 1 times x minus 1. We get x equal to negative 1 and x equal to positive 1. And this one will have nothing. So if you set this equal to 0, right, you'd have x squared equals negative 1. So you wouldn't get anything out of it because x squared won't equal negative 1. So the only two things you have to use on your sign chart are going to be 1 and negative 1. So looking here, plugging in negative 2 to x plus 1, you'd have a negative. Negative 2 minus 1, you'd have a negative. And then this one will always be positive because if you square a number, the smallest that'll be is 0. Like 0 squared is 0, but if you add 1, it's positive. So this will never be negative. This will always be positive. 2 negatives make a positive. For x equals 0, we have positive, negative, and then the last one's always positive. For x equals 2, we have positive, positive, positive. So that's positive. So increasing, decreasing, increasing. So we are increasing from negative infinity to negative 1. And from 1 to infinity, we are decreasing from negative 1 to 1. We don't have any asymptotes, so we can just kind of do a little sketch in here to see that there's going to be a max at negative 1 and then a min at positive 1. To get the y values for these coordinate points, because what I'm really doing here is I'm saying if negative 1 is the max for the x value, we have to get the y value. The original function, one more time, let me bring that down here so we can look at it. So plugging in negative 1 to this function, let's see, you're going to have negative 1 plus 5, that's 4, plus 1 is 5. And a min at 1 plugging in 1 there, you have 1 minus 5 is -4 plus 1 is -3. So you have all that information. And I know these are tedious. They take some time. So what can I do here to see if I can maybe shrink this, and I want to put this all on one page. There we go. Then for concavity and inflection points, we take the second derivative and we're making another sign chart. When you're taking this second derivative, I highly suggest going back to the unfactored form of the first derivative. Otherwise, you're going to end up doing some pretty nasty like product rule. So just go back to the original version of your first derivative. And from there, you're going to get 20x cubed. And we're setting it equal to 0. The only way for that equation to work is if x is equal to 0. So that's the only point we have to worry about. If you plug in -1, you're going to get a negative. If you plug in 1, you're going to get a positive. Because this is the second derivative, we're talking about concavity. If it's the second derivative and it's negative, that means you're concave down. And concave down are sad people. Those are people who are down all the time. And positive are positive, happy people who are up, concave up. So we are concave up from 0 to infinity. We are concave down from -infinity to 0. And because we change concavity at 0, that is an inflection point. So we have an inflection point at x equals 0. And when you plug 0 into the original function, that one right up here, you're going to get 1. So altogether, we have this information. So I'm going to make a new page and paste all of our information from this page onto the next one so that we have it all in one place. All right, is it pretty? No. Does it work? Yes. I'm going to stop and restart recording, just once again, just in case things corrupt again. All right. So I'm going to hand draw this graph, and we're going to do the best we can. Now, I noticed that my y values and my x values, so my x values are pretty small, right? Like I have like 0.2, -1.5, 1.4. So my x values really only need to go up until like -2 maybe. So if I put -2 here, put -1 here, so it'd be -2.5, -0.5, and then similar thing over here. My y values are also pretty small. If we look at the y values, like my maxes and mins, I need a 5 as my biggest y value. I think -3 ends up being your smallest y value. So 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. Somebody said, shouldn't it be -1.5? Yeah. That's why I need you guys. Don't trust my brain. Thank you, I appreciate that. All right. So I'm going to stop for plotting points. So I'm going to plot my x-intercepts. So 0.2, comma 0, somewhere like around here. -1.5, comma 0.9, somewhere around there. That's it. What happened here? Why are those x-intercepts? Those x-intercepts don't make sense. Why? So give me a moment, guys, because those x-intercepts don't make sense, because if those were the x-intercepts, they wouldn't have, these would be zeros. So I think it's because of the way I rounded them. I don't know why I plugged those back in. That was silly. Those should be zeros because they are x-intercepts. Yeah. It's because I rounded them. So like this guy originally was -1.54165, and this was this is positive 1.4405. These should be zeros. They should have been, that's why they were close to 0, was because they were rounded numbers. They should be x-intercepts. So these should be zeros. I don't know what to say. My pregnant brain doesn't work as the way that it used to. These are x-intercepts, guys. 1.4. You don't plug back in for the x-intercepts. My y-intercept is 0, 1. And then my other points I have to plot are my maximum at -1, 5. My minimum at 1, -3. And my inflection point at 0, 1, which is already plotted. So then I am breaking up my line, I'm going to draw a chart underneath using the x values. Let's use red here. Using the x values where the concavity and increasing, decreasing break up. So increasing, let's see, we have -1, so I'm going to just kind of draw. This is like a line just to help me draw my graph. And at 1, these aren't asymptotes or anything, just here to guide me. And at 0. So I have -1, 0, 1. And we are then taking our information from increasing, decreasing. Oops, let's see here. From increasing, decreasing. So we are increasing from -infinity to -1, and from 1 to infinity. We are decreasing from -1 to 1. We are concave up from 0 to infinity. And we are concave down from -infinity to 0. So now we have all that information there. Woo! So the picture, like I said, with the concave up and increasing, decreasing, I like to just kind of like split this guy in half and then decide which side you need. So if you are increasing and concave down, the side that's increasing and concave down is this side here. The side that is decreasing and concave down is this side. Decreasing concave up is this side. Increasing concave up is this side. So my picture would look like this, like this, like this, and like this. So for this portion right in here, this entire portion, it needs to have this type shape. And I need to hit all the points that I already have. So I'm going to have like this type shape. And this point got plotted weird because this point was supposed to be at -1, 5. So that point should be right there. I'm going to make it a little more round here. You don't have to be a perfect artist about it, but like if you know, because I know it's going to be a maximum, so I want it to kind of be nice there. And then from -1 to 0, you want it to have this shape. So you want it to have this type shape all the way up to 0. Then starting at 0 and going until 1, we want it to have this shape. So it starts to make this kind of caving type shape. And then from 1 to infinity, it has this type shape. And that's more or less what the graph ends up looking like. So once again, you're not plugging in for these x-intercepts. You're not plugging in. Don't do this. Don't do that. Do just this. It's zeros for the x-intercepts. And that was the result of rounding. So I'd like to do one where everything is already factored, and that way, like, it saves on some of the math part of it, and that way you can just kind of do the problem. So I'm going to give you guys one to try, where I'm going to give you I'm going to give you f, I'm going to give you f prime, and I'm going to give you f double prime, and they're already going to be factored, so you don't have to worry about doing the math. You're just going to have to do the x-intercepts, y-intercepts, asymptote, domain sort of thing. So maybe we'll do this in kind of steps. So I'm going to give you f of x is equal to x over x plus 1 squared. Like I said, you're not going to take these derivatives. I'm just going to give them to you so you don't have to do them. Wait, should I get? Yeah, that one. That one's right. Yeah. All right. So once again, as a reminder, this first one you're using for figuring out asymptotes. There will be an asymptote here. You're finding asymptotes, x-intercepts. X-intercepts are when the numerator equals 0. If it's a rational function, numerator equals 0. You're going to need to find horizontal asymptotes. And then x-intercepts, y-intercepts, horizontal asymptotes for this guy. Using this guy, the second one, the first derivative, you're going to find increasing, decreasing maxes and mins. And then using second derivative, you're going to find concavity. So I'm going to give, I don't know, let's say I'm going to give 3 minutes just to find the first part, which is intercept or domain / intercepts / asymptotes. So I wrote down the directions here. So I'm going to put a 3.5 minute timer on. All right, so hopefully maybe you've gotten a little bit further than just this part here, but I'm going to go over the first part. So for the x-intercepts, if you set the numerator equal to 0, you're just going to get x equal to 0. So that's going to be 0, 0. For the y-intercept, if you plug in x equals 0, you have 0 over 1 squared, which is 0. So I think I've said this before. If you have the x-intercept 0, 0, you have the y-intercept 0, 0. If you set the denominator equal to 0, you're going to get x equal to -1. So there is a vertical asymptote at x equals -1. And then for the horizontal asymptotes, you're taking the limit as x approaches infinity of x over x plus 1 quantity squared. We can FOIL out that denominator, and then we can eliminate all but the highest power. So we have x squared plus 2x plus 1. And then because we're going to infinity, we're eliminating everything except for the highest power. So we have x on top, we have x squared on bottom. So we have the limit as x approaches infinity of 1 over x, which would be 0. And in the other direction, as x approaches negative infinity, the simplification would be the same, right? The simplification would be the same. You'd still get 1 over x, and you'd also still get 0. So we have a horizontal asymptote at y equals 0. So for the next part, you're going to be doing increasing, decreasing, max, and min. And you are using this derivative that's already been taken for you. So don't take it yourself. This is the derivative. Right? So you're going to make a sign chart. You're going to find your maxes and your mins. And then you're going to find increasing, decreasing. So I'm going to give, I think, 3 minutes for that. It shouldn't be as bad because you don't have to actually take the derivative or factor it. All right, so looking at increasing, decreasing max mins, you want to look at places where the denominator is 0 and where the numerator is 0. So we have -1 and 1. Now, something to note is that -1 is our vertical asymptote. So I'm going to kind of make a note here about that because -1 can't be a max or a min. That's important because there's a vertical asymptote there. So x equals -2, x equals 0, x equals 2. And then plugging into f prime. 1 minus -2 is a positive. -2 plus 1 is negative. A negative cubed is a negative. 1 minus 0 is a positive. 0 plus 1 is a positive. A positive cubed is a positive. 1 minus 2 is a negative. 2 plus 3 is positive, so a positive cubed is a positive. So we have a negative, positive, negative. So decreasing, increasing, decreasing. So we are increasing on -1 to 1. We are decreasing on negative infinity to -1 and 1 to infinity. We have a max, so we can't have any maxes or mins at the asymptote, but we do have a max here at 1. And if you plug 1 back into the original function, so the original function is x over x plus 1 squared, you're going to have 1 over 2 squared. So you're going to have 1/4. and no minimum. So far, how is this going for everybody? Good, good. Excellent. So I'm going to scroll it back up so that you can see the F double prime. And I'm going to give another let's do 2 minutes. I'm going to give you 2 minutes to do the concavity. So you should be doing concavity and inflection points. Oh, somebody asked, where did the -1 and 1 come from for the chart? So if you look up here, you're looking at F prime, and you're looking at places where the numerator and denominator are 0. So if you set the numerator equal to 0, you get x equals 1. And if you set the denominator equal to 0, you'd get x equals -3. Or not -3, -1. -1. I was looking at the cube. -1. Does that make sense? Yeah, no problem. No problem. And you'll be doing that same thing with F double prime. So I'm going to set 2 minutes and F double prime. All right. So with your concavity, you should be using x equals 2 and x equals -1. Once again, for -1, you do have an asymptote there. And you are plugging in to F double prime here. So -2 minus 2 is a negative, and then because the denominator is raised to the 4th power, it'll always be positive. So it's going to be positive in all of these. And then if you plug in 0, 0 minus 2 is going to be negative. Plug in 3, 3 minus 2 is positive. So we have a negative, and then a positive. This is concavity, so we are concave down, concave up. So I'm going to write concave up like this. We are concave up from 2 to infinity. We are concave down from -infinity to -1, and from -1 to 2. You can't write this as one singular interval because there is an asymptote there. Inflection points happen at places within the domain where concavity changes. So concavity changes at 2, and 2 is in the domain. The only number not in the domain is -1 because of the vertical asymptote there. So there's an inflection point at x equals 2. And if you plug 2 back into this original up here, you get 2 over 3 squared, so 2/9, which is approximately 0.2. And that is your concavity information. So at this point, you should be sketching your graph. I'm going to give you time to do that while I compile all this information and move it over to the next page so that it's all in one place. So draw your graph right now, and while I compile this information. All right, so I am going to start putting together my graph. I'm going to kind of make my x values kind of far apart. And my y values are also going to be kind of far apart because we have pretty small numbers here. So I'm once again going to draw some really light lines where I want to break stuff up, and then I'll come back and do my asymptotes as well. So I want to, I meant to draw this line. I meant to draw this, oops. I was trying to separate the points from the intervals so that it was clear which ones were points and which ones were intervals. And I accidentally didn't include the inflection point. So let me do that. So I have this grouped so that all of the intervals are down here and all of the points are up here. So when I'm breaking up my graph to draw my chart underneath, I'm breaking up at -1. These are just really light lines you're drawing on your paper to help guide you. At 1, got those, and at 2, and also -1 we've already done. So underneath here, at -1, we're going to have an asymptote, so I'll draw the asymptote line there. So I'm just making that ready for myself. All right, now we'll start with the asymptotes. So we have a vertical asymptote at x equals -1, so I'm going to draw that in. We have a horizontal asymptote at y equals 0. So when it's at y equals 0, you kind of have to be aggressive with your dashed lines. For the points, I have an x and y intercept at 0, 0. I have a max at 1, 1/4, so somewhere up there. A inflection point at 2, 2/9, and this is like 0.2-ish. So like this. However, because these are so close together, I'm just going to go ahead and put him up a little higher just because he's supposed to be a max. So I'll move him down a little. They're very close together though. So those are all the points I can plot. Now I can go for the intervals. So I'm increasing from -1 to 1. And I am decreasing from -infinity to -1 and from 1 to infinity. I am concave up from 2 to infinity, and I am concave down from -infinity. Wait, what those intervals don't make sense. Hold on. Oh no, oh, I see. Yeah, it was broken up because of the asymptote. Just kidding. They make sense. Concave down and then from -1 to 2. Cool. So if you are decreasing concave down, that means you are this part. Increasing concave up, that's this half. Decreasing concave down, you are this half. And decreasing concave up, you are this half. So you are this picture, this one, and then this one. We know that we have to hug the asymptotes. So coming in here, we're going to need to hug the asymptotes. We need to hug the horizontal and we have to hug the vertical. So the only place where this could go, it couldn't go up here because you couldn't make this shape. It wouldn't work with the asymptotes. Only place you could put it would be possibly right here. So that will be this piece. Right? And then in this entire region, we are making this shape. So we know we're making something like this and hugging the asymptote. From there, in this piece right here, we want to be kind of concave down. So, it's the best you can do with so little space there. And then for this piece, you have to hug the asymptote. Oops, you have to hug the asymptote and it's making this shape. So it's kind of like just scooping down and then going out. So it's like scooping down and going out. And it doesn't really cross again, it just kind of gets close. Right. Can I answer any questions or comments about this one? This one would have worked a lot better if I had done a different scale up here. Like if I had done 1 right here and done like 0.5. This would have worked a little bit better. Even still, these points would be still close together. But at least it's something. So hopefully that practice helps a little bit there. All right. Just wait seeing if there's any questions before I move on to the next one. Well, the next section really, because we need to talk about optimization today. Good. I'm glad. Yeah, the asymptote part, it helps a lot. It helps when you have it already factored and stuff. The thing is, like, you can't really do asymptote problems without having nasty factoring with the first and second derivative. So it helps when the first and second derivative are already done for you so that you can do the asymptotes and not have to worry about the headache of, you know, the factoring and the messy algebra. So I guess with that all in mind, we will move on to optimization. So I said earlier when we were talking about related rates that there were 2 word problem sections. One of the sections is related rates, and the other one is optimization. So optimization is different than related rates in that related rates talks about different rates and how they work together. So like, you have a ladder falling down a wall. How does the rate at which it falls against the wall versus the rate at which the bottom of the ladder expands from the wall, how do those relate to one another? Optimization involves optimization. It involves optimizing something. How can I get the most bang for my buck? How can I maximize my profit? How can I spend the least amount of money on fencing but get the most amount of area? It's questions like that. So you're making something small, you're finding the smallest or largest amount of something given a constraint. So with these problems, you want to read them carefully. It's sort of like what I said with related rates. You got to read the problem. You got to read it. You got to read it. You got to read it. So it's easy to get related rates problems and optimization problems mixed up. So some things to look for. In an optimization problem, there's going to be some keywords like the word, oops, this is big now, like the word optimize or the word maximize or the word minimize or largest or smallest. That's another giveaway that it's an optimization problem. So you're looking for those kind of keywords to know it's an optimization problem. They end up being similar, but they are different. They are definitely different. If you can draw a picture, you should definitely draw a picture. Not all problems you'll be able to, but some of them you will. The next part, you're going to be given information about a problem, and there's going to be 2 equations involved in it. You're going to have an optimizing equation and you're going to have a constraint equation. So the optimizing equation is the quantity you want to optimize. So if you're trying to maximize profit, your profit equation is your optimizing equation. If you're trying to maximize area, area is your optimizing equation. This is the quantity you want to make smallest or biggest. sometimes this optimizing equation, oftentimes, this optimizing equation is going to involve two variables, and you need to use this constraint equation I'm about to talk about, and you'll use substitution with this constraint equation. This constraint equation involves a constraint. So essentially, if you're asked to if you're fencing in a field and you want to make the largest amount of area, if somebody just says, I want a fenced in field where the area that's fenced in is largest, you just say there's no answer to that because I can make my fence as large as you need. If you're not going to tell me how much fencing I have, then I have all the fencing in the world and I can make my fence huge. I can make it, the entire world gets fenced in, So a constraint would be like, well, you make it the largest area, but you only have 200 feet of fencing. Make it the largest area, but you only have $700 to spend on fencing. It's stuff like that. It's what constrains you so that when you're maximizing or minimizing, there are bounds which you need to stick within. And this allows you to write one variable in terms of the other so you can plug it into the optimizing equation. So your first step is reading step 0, reading the problem. Step 1, draw a picture. Step 2, write down the relevant information. In particular, write down the optimizing equation and the constraint equation. The next step is if you have a constraint equation. So not all of them will have a constraint equation, but if you have a constraint equation, you use it to make a substitution into the optimizing equation. And that way you'll only have one variable in your optimizing equation. After that, because you're trying to find a max or a min, we know we can find maxes or mins using the first derivative, right? We can find the derivative, make a sign chart, or use the second derivative test, and we can find a max or min. Here's the thing you have to be careful about. Sometimes things have multiple maxes, so you need to make sure that you're finding the right max. Sometimes you're going to have endpoints, and if you have endpoints, you need to verify those endpoints, like we did with the extreme values, where we tested the critical values and then we tested the endpoints to find which one was the biggest and which one was the smallest. So you need to verify which is the biggest and which is the smallest, and you will get marked down if you don't verify. Even if your answer is correct on a test, even if it's correct, you will get marked down even if you do not verify the max. I'm going to show you me doing that. So I'm not just saying it out loud. You'll see me doing it. And as necessary, round answers to 2 decimal places for this section. So here we go. The classic optimizing problem. A ranch has 200 feet of fencing, which is used to enclose 2 adjacent rectangular plots that will share a fence. What dimension should be used? This should be so that the enclosed area is maximized. And it's saying the enclosed area is maximized. That's where we know it's an optimization problem. These aren't rates, right? It's asking for an optimized area, maximized area. So we're going to start, we read the question, we're going to start by drawing a picture. So we are trying to enclose 2 adjacent rectangular plots that share a fence. So they're rectangular plots, they share a fence, so it's kind of like you have one big plot, and in the middle they have a shared fence. Now we are going to need to label these side lengths at some point, so I'm going to give myself a little bit more room here. So step 2 is writing down relevant information. We know that we have 200 feet of fencing. So the total perimeter of this lot, of this these plots, the total perimeter should be 200 feet because that's how much fencing we have. And we know how to find perimeter. You just add up the side lengths, right? So I can label these. It doesn't matter what you label as what. You could label this guy as X. So if that one's X, these are X's. And this whole thing here would be Y. So if we add up all of these sides, that would be our perimeter. So we have 3 x's. So 3x plus 2y's is equal to 200 feet. This is our constraint equation. It's telling us that that's what is constraining you. You have 200 feet, that's the max that you have. You're not trying to optimize perimeter, that's just how much you have. This is our constraint. What we've been asked to optimize is area. So if we're maximizing area, and the way that we're going to view area in this case, we're going to view, if you add these two together, like the whole area of this entire closed in. It's like 2 areas in one, but we're just going to maximize the total area in here. So area is equal to, if it's a rectangle, this would be X times Y, right? That's the area of this rectangle, X times Y, area of this entire rectangle. And that is the optimizing equation. Your next step is using the constraint equation to make the optimizing equation one variable. Because the problem right now is that our optimizing equation has 2 variables in it. So we can't really take a derivative. If we did, we had multivariable, it would get weird. It's not like related rates. We don't have a bunch of rates sitting around. So we want it to be one variable so we can just take the derivative the way we're used to taking derivatives. So our constraint equation was 3x plus 2y equals 200. Right, this is our constraint. Our optimizing is area equals x times y. So we have to either solve for x or solve for y. It doesn't matter which one you solve for, and we'll figure it out in the end. I'm going to choose to solve for y here. Here's my thought process and why I'm solving for y. Because I know if I solve for y, I'm going to have to divide by 2, and at least I know that 3 isn't divisible by 2, but I know 200 is. If I solve for x, I'm going to have 200 divided by 3, so that's just a little bit more fraction work than I want. So I'm going to subtract 3x on both sides. I get 2y equals 200 minus 3x. And then I am dividing both sides by 2. And I get y equals 100 minus 3 halves x. This equation right here gets plugged in for y in this equation. And if we do that, so if we, instead of putting y, we put 100 minus 3 halves x. Then this is going to be an equation that just involves x's. So we'd have 100x minus 3 halves x squared. So I guess this is actually step 2.5, so I should write 2.5 here instead of step 3, if we're using these steps on the front page. Step 3 is taking the derivative, finding the critical values, and making sure that the critical values give us a max. So taking the derivative of area, using this area equation down here, we have 100 minus 3x. We want to find the critical values, so we're setting this equal to 0. Right? If you solve for x here, you're going to get x equals 100 over 3 feet. That's the only critical value you get. Now, you have choices on, so hopefully this is the answer, right? This is hopefully our answer, but we cannot do anything until we've verified that this is a max, right? If you do not verify, even though this is the only answer you get, if you do not verify, you will be marked down. So to verify, you can either do the first derivative test. The first derivative test would be making a sign chart, and you would only have one value, so you can make a sign chart. Or you can do the second derivative test, where you take the derivative and then plug the second derivative and then plug in the x value. So with the second derivative test, it ends up being a little easier here. If you take the derivative of a prime, you get -3, which is negative. And if your second derivative is negative, that means you are concave down. And concave down is this shape, which means you would have a max. So either verifying using first or second derivative test. First derivative test is the same thing we did over, let me go back page. The first derivative test is this guy right here. Second derivative test is taking the second derivative. But double checking that what number we got was a max. We want to make sure it's not like a min. Your step 4 is giving the answer. So we wanted the dimensions. We want to give x and y. And we were told to round our answers to 2 decimal places. So 100 divided by 3 is going to be 33.33. To get y, so this is our x. To get y, you plug your x value back into your y equation, because your constraint equation. So 100 minus 3 halves times 100 over 3. This is going to give you 50 feet. And that is that. So oftentimes students like the optimizing a little bit more than the related rates because you're not dealing with implicit differentiation. And I would say that in many cases, not all, but many cases, the setup is a bit nicer. Now, like I said, not always the case, but sometimes the case. Any questions on this first example before I go through another example? If not, I will just scroll down. We'll go on to the next one. So for this one, you're trying to find 2 positive integers such that the sum of the first number and twice the second is 108 and their product is a maximum. I know this sounds like a lot, but when you write it down, it's not going to be that bad. So the important part, figuring out what you're optimizing. So it says their product is a maximum, right? Their product is a maximum. So we should have a constraint equation and an optimizing equation. For the optimizing, we want this to be the product of the 2 numbers. We have 2 numbers, we want their product to be the maximum. So a product is going to be multiplication. So if I have 2 numbers and I'm going to call them x and y probably, because x and y are just, common, but you can call them a and b, call them whatever you want, whatever makes your heart happy. X times y. That would be what I'm trying to optimize. The part that's the constraint is that the sum of the first number and twice the second is 108. Sum means that we're adding them up. If the first number is x, so we want the sum of the first number and, so x plus twice the second, so 2y, twice the second is 108. That's our constraint. So we want to solve for x or y, plug it into the optimizing, take the derivative, find the critical values, and then find the 2 numbers. I'm going to give you a chance to try this. This is the same process as before. It's a very similar problem as the last one. I'm going to tell you that it's going to be easier to solve for x here. So if you get x by itself here, that would be easiest, and plug it into here. Take the derivative, try it out. I think you can do it. I think it's going to be okay. So I'm going to give you 5 minutes to try that out. working on that answer. So for this guy, I'm choosing to solve for x here. So you'll get x equals 108 minus 2y. I'm plugging that into the product equation. So I have 108 minus 2y times y, which gives me 108y minus 2y squared. I'm taking the derivative of that function. I get 108 minus 4y. Setting that equal to 0, you'll get 4y is equal to 108. So y is equal to 27. At this point, you want to make sure that this is a max. So we're going to verify. It is easiest here to do the second derivative test. So I'm going to do p double prime. Gives me negative 4, which is less than 0. So it's negative, which means we are concave down, which means it's a max. For a lot of these, the second derivative test will be sufficient, and I highly suggest doing it. When I say that you need to verify, I don't mean to write any more than this. This is about all you need to write. Take the second derivative, draw me that little rainbow shape or the cup shape, whichever one it ends up being, and then verify max or min. That's what I want. Then for x, you're plugging back into this equation you had up here. So x equals 108 minus 2 times 27, which should give you 54. So the two numbers that you should get are 27 and 54. Is that what everybody got? Yes, excellent. Yay. Great. So we're all having a good time then. That's the first time I feel like I've seen like a really triumphant yes from so many people. That makes me so happy. Oh, great. Excellent. So we are going to go ahead and do this next problem. I'm gonna do the setup part of it. And then I think I'm going to have you guys try it. It's going to be okay. The setup for this one is the weirdest part. And you may have seen one of these ones before because they do them in Math 126 sometimes, but you don't use calculus. You use like a graphing calculator instead. But here's the setup. A box with an open top is made by cutting small congruent squares from the corners of a 20 by 20 sheet of tin. Is that foot? Yeah. 20 foot by 20 foot sheet of tin and bending up the sides. How large should the squares cut from the corners be to make sure the box holds as much as possible? Now, when we're in person, I use visuals, but unfortunately we are not. So I'm just going to do the best I can to draw this. So you start with a square sheet of tin. Right, this is my square sheet of tin. And you want to cut small congruent squares from the corners. The congruent means that these are all the same size. And then what you're doing, what you're left with, so you take these squares out and you're left with this kind of like plus shaped thing. You fold up the sides to make an open box. If you have a piece of paper, you can try it for yourself. So you tear out these corners and then you're left with a shape that looks a little bit like if I were an artist, it would look much better. Like this. All right, I'm not an artist though. I just do my best. And these little flaps get folded upward, and this is the bottom of the box. So these flaps get folded up, think in 3 dimensions right now. They get folded up, and then you have a box. It's an open top box. So we cut out those little corners. We have a box left. We need to look at what we want to optimize and then what our constraint will be. And sometimes the constraint, I guess they're both important, but you can't do anything with the optimizing until you have a constraint, if there is going to be a constraint. And in this case, there is a constraint because we have limits on our how big our box is. So I'm going to label some stuff. I know that these little squares I cut out are the same size, so I'm going to label that side length X. So because these are squares that were cut out, this is X on each side. And then I'm going to label these ones, this length Y. In terms of constraint, we know that this is 20 feet long. This is 20 feet long. And if you look at my little diagram here, so this is a little square X down here, right? So this right here is length X, this right here is length X, and then this right here is length Y. So we know if we add all those together, they have to be 20 feet because that's how long this side of the aluminum box is. So our constraint is 2x plus y equals 20. Now, there's another constraint we have to worry about here because there are limits to how big x can be. There are limits to how big x can be, or how big y can be. You can limit it either way, but the limit is if x were any greater than 10 feet, so x can't even be 10 feet. If x was 10 feet, you would be cutting out the entire sheet, right? If you had 10 feet x squares here, there you'd be left with no aluminum. So something to keep in mind domain-wise, x needs to be greater than 0, but it needs to be less than 10. If we're talking about y cannot be 0, right? We can't have it as nothing in the middle here. So it has to be bigger than 0. And it can't be bigger than 20, because if it was bigger than 20, then it wouldn't fit on here. So those are not including those endpoints. So just something to keep in mind with our answers. We want to make sure that the answers we get fit within these guidelines here, just that are common sense guidelines. Like you can't make a 10-foot cut out of this box. You can't make a 0. You're not cutting nothing. These are just the common sense kind of constraints, domain constraints. Meanwhile, what we are optimizing is the volume. The volume of a box is length times width times height. When you fold up this box, these x's are going to become the height of the box. Oops, x. Because these little flaps fold up, and then that's the height. The length of the box comes from here, so that's y. And same thing with width. This is the width of the box. Maybe I should do that in blue. The width of the box. And that is also y. The setup here is the hard part. So you have y times y, right? Y times x. So you have y squared x, which I'm going to write that as x y squared because that's what makes my heart happy. So you have options here. In the end, what you want is you want to know how large the squares should be to make the box have as much volume as possible. So you want to find x, so you can solve for y here, or you can solve for x. Because you want to find x in the end, solving for y is easier because you end up with x's. But you could do either. I've never actually done this problem where you solve for x and then have y's at the end, so I'm like tempted to do that just since it's something I've never done before. But maybe I'll just solve it the way I normally solve it. Or maybe I'll go off on a limb. No, we'll just solve it the way I normally solve it. All right. So I'm going to solve for y here. It'll be boring. I'm going to solve for y. Then what I'm going to do, I'm going to plug in this y in my volume equation. So I have v equals x times 20 minus 2x, quantity squared. And I was going to let you guys finish the rest of this problem, and I realize I've already done it. You know what? You could do it this way or do it with solving for x. So here are your options. I'm going to give you options. Either you're using this constraint, or you can use the constraint x equals, let's see, 10 minus 1/2 y. But use those constraints. I'm going to make suggestions. So if you're going to go this route, I suggest foiling this all out before taking the derivative. You can do it without, but I just suggest foiling it. It might make it a little nicer. And then for this one, you won't have to do any foiling. So make a decision on whether you want to use this equation and do this, or your other one would be you would keep the y squared, but you'd plug in your x part right there. Right. I'm going to give you 3 minutes to work through this. Yeah, so I have 2 minutes to finish it up. So there's still like 20 seconds on the timer, but I want to kind of start writing through it so we can get through this problem. I kind of want to go through both ways because I think I can do it quickly enough. So if you FOILed this out before taking the derivative, you're going to get 400x minus 80x squared plus 4x cubed. So taking that derivative, you get 400 minus 160x plus 12x squared. You should be able to factor a 4 out of this. So factoring a 4 out of it, I'm going to put this up front, 3x squared minus 40x plus 100. The factoring on this one might be slightly messy, I guess. But this one comes down to, let's see here, x minus 10. Yeah, x minus 10 and 3x minus 10. So you get two answers. You get x equals 10 and x equals 10 over 3. Now, only one of those answers can work, and that's why it's important to go back here and look at the domain. So x can't be 10 because 10's not in the domain. So the only real possibility we have is for 10/3. If we verify this with v double prime, I'm going to take this derivative from here. We get negative 160 plus 24x, and then you'd plug in 10/3 to that derivative. Times 24 times 10/3. So let's see, negative 160 plus 80. Oh, so negative 80, which is less than 0. So we are concave down. So we have a max. So x is equal to 10/3, which is approximately 3.33. So the square should be 3.33 feet wide. For people who went the other route, which I've never done before, where you plug in 10 minus 1/2 y times y squared, you get 10y squared minus 1/2 y cubed. Take that derivative. You get 20y minus 3/2 y squared. Set equal to 0. You can factor out a y. So you have 20 minus 3/2 y equals 0. You get y equals 0. That clearly can't be the case. You can't have y equal to 0 because that doesn't make sense. Then the other one, you would get 3/2 y equals 20. And let's see, multiply by 2, divide by 3, 40 over 3. So y equals 40 over 3. And then because you want the x value, you would go ahead and plug that back into this equation here. So x would equal 10 minus 1/2 times 40 over 3. So 10 minus 20 over 3, which hopefully is 3.33. And you'd need to verify it as well. I'm just being lazy here. The factoring here is kind of annoying. Technically, you can do this with product chain rule, but you have to do a little bit of tricky factoring. It's just, you can get it down here. It just takes a little bit of time. Can I answer any questions for anybody about that problem? If not, then we will do, I think, one more optimizing problem on Monday. And so I'm going to end up skipping the next two optimizing problems because they're number 5, 3.5.5 in particular is a pretty challenging one. And it has really, really messy algebra that I just don't want to talk about. So I do want to do the last example of this section. So we'll do that on Monday. Then we'll start talking about antiderivatives, and then we will be doing an exam review on Wednesday. So I'll get that exam review out sometime early next week. And then the week following, so not next week, but the week after, that'll be exam 3 week. And I think very close to Thanksgiving. Let me look at the calendar again. Oh, our calendar doesn't show Thanksgiving. Well, regardless, we're getting close to Thanksgiving. This is something I'm very excited about. The 26th. Okay, let's see. So exam 3 we do, I guess, 2 weeks before Thanksgiving. Thanksgiving's really close to break. Thanksgiving is really close to break. Oh well. Regardless, on Thanksgiving, so we don't have class on Thanksgiving, obviously, because we're a Wednesday class. On November 25th, I will have to do a lecture that day, but like always, I'm going to record it, and I'll be lenient with the homework that weekend, the Thanksgiving weekend. So if you need longer to turn in the homework over Thanksgiving weekend, that'll be fine. And I will record and make sure that the recording holds for the Wednesday. So if you're cooking, that you don't have to worry about actually attending. And that is all. I've already gone 6 minutes over. So I appreciate you all being here. You guys are all awesome and excellent. Somebody said they really liked this unit, and that makes me happy. Not the last one. That's okay. You don't have to like the last one, but the optimizing is fun. It's kind of like the related rate stuff. I agree with you. I like the optimizing stuff a lot. So homework is posted. If you have questions, let me know. I will be so I don't have any optimizing homework posted yet. That one will be next week's homework. So for now, if you want to practice, if you want to try the other examples in this section, like the 3.5.4 and number 5, you could try those. They are going to be a little bit on the more difficult side, but you could try those ones out. Otherwise, practice the curve sketching stuff, and I will see you guys all on Monday.